Now I want to explain you an alternative proof, or the idea of an alternative proof for the direct proof of the channel coding theorem. So we assume that we have a discrete memberless channel and we want to send messages over the channel. Shannon's idea was to select randomly typical sequences as code words. But how many code words can we select? So therefore, we look at the size of each conditional typical output set. So if you choose some typical sequence, then the conditionally output set has the size 2 to the n and the entropy of y conditional on x. So, and in totally, we have the size of typical sets of all output sequences is 2 to the n h of y. Now, if we look now how many messages can be used, so we just divide the output typical sets into m conditional typical sets, and so we be able to distinguish 2 to the n h of y divided by 2 to the n h of y conditional on x. And if you look at this, this is equal to 2 to the n times the mutual information of x and y. And as you know, this is exactly what we want. So what Shannon finally did, he showed that this works. So we can randomly choose some typical sequence as decoding set for the receiver. We just choose the conditional typical output set for the chosen sequence. And totally, we have so many output sequences. And in this way, he showed the direct proof of the channel coding theorem. Another remark I will give you is for entropy typicality for Gaussian variables. So we already remind you that for entropy typical sets, everything, not everything, the standards definition can be done also with the differential entropy and for Gaussian variables. Now let's see first. Let's see what this means. We know we have this density for Gaussian random variable. We know what the expected value is, and we know what the variance is. Then we know that this formula here is exactly the definition of entropy typical set, entropy typical sequence. So xn is called entropy typical sequence if this is fulfilled. But now we can reformulate it just by putting in the definitions. So we're putting in the density, the expected value, and the variance, and then we see that this is equivalent to this definition. So instead of using the same definition like in the discrete case, and then we can directly use this definition here. But what is with the other definitions? Let's, for example, look at entropy, jointly entropy typical. So in the discrete case, we can just replace, we just have to replace the differential entropy with the Shannon entropy here. But you see, in the discrete case, we just have this formula, 47. But now, in the continuous case, for Gaussian channels, we need all these three equations. You see, you need here that y is typical and x is typical, and also xy, the joint random variable, is typical. The reason that we require all three conditions is that 46 and 45 does not follow from 47. That's the main difference.